Okay, so this is the KITS session, KITS Reconnection, MESO, CEDAR. I think those are all the groups co-organizing this. Session on substorm onset. We're gonna have 4 speakers. They each have 20 minutes to talk, but we're gonna start off with Jason Durr. He wanted to just introduce the topic to everyone. So Jason, why don't you take it away?
All right, sure thing. Can everyone hear me?
Yes, we can hear you.
Awesome. All right, so yeah, the session is focused on substorm onset. Basically, the question we're trying to broadly pose is how to make progress on the topic. All right. So some of the more specific questions are what triggers the onset of the substorm expansion phase? That's what we mean by onset. What clues can we get to tease apart all the different mechanisms from theory, magnetospheric and ionospheric modeling, satellite observations, and ground observations? How can we rule out certain potential mechanisms instead of just having this proliferation of different proposals? How does the preconditioning of the magnetotail influence substorm onset? What's the location? What's the connection between magnetotail and auroral observations? And then in general, we kind of want to both examine the standard mechanism proposals and maybe bring up some of the less frequently discussed mechanisms to see whether there's something promising there that hasn't been addressed frequently enough. Minna Palmroth was going to be part of this discussion, but was unable to make it in person, so she just sent me a few slides to read on her behalf. I basically condensed it down into one. So this is her comments on modeling specifically. Her idea is that basically we need a self-consistent ion kinetic global simulation coupled to a proper ionosphere, and that's basically the next step. This is broadly in line with the general KITS idea. Why global? Well, substorms are a global process driven by dayside reconnection, and local simulations tend to have artificial boundary conditions as a result of neglecting what's going on outside of the region. Why the entire simulation box? We don't know where in the box the onset process is initiated, so it's not sufficient to have only a part of the box reproducing ion kinetic physics. These are, again, Minna's comments. We're free to all have discussion on which of these are true and how they pertain to substorm onset. Why ion kinetics specifically? Paradigms have been suggested based on observation that include ion kinetic physics, especially instabilities that can't be modeled with simulations that neglect ion kinetic physics like MHD simulations, and modeling reconnection doesn't appear to be sufficient on its own. Why not electron scale? Basically, the idea is that we're not really at that stage yet. They seem to be impossible in the foreseeable future. And why a proper ionosphere? We don't really know what role the ionosphere plays, and some suggestions like Runoff 2021 seem to suggest it's important for current sheet thinning. I mean, there's also the obvious impacts of conductance. All right, I believe Harry went over the rest of this. I did just want to say maybe it would be useful to have the speakers indicate in advance whether they'd like interruptions by other panelists during their allotted time. I don't know to what extent we want it to be discussion between the panelists. I guess each panelist can just sort of decide that on their own as they give their talk. But then after each 20-minute presentation, we're going to have 5 minutes for discussion. We also wanted to advertise the poster sessions that are tomorrow and Wednesday from 3:30 to 6:30. And we've got 6 different KITS presentations, 3 in each of those. So urge you to check those out. And that is all of the comments I have. So we'll turn it over to the panel.
All right, thank you, Jason. So unless anybody wants to jump in with a comment already, I think we can let Larry give his talk.
Jason, can you stop sharing your screen?
Sorry about that. There we go.
Thank you.
Just the cursor.
Use a cursor so the online attendees can see this.
Oh, okay. Oh, I should have brought my glasses up, man.
Just so you know, online we can still see your notes.
Let me see. I don't see, I have the cursor there. Okay.
All right, looks good online.
So this is a quick outline of what I'm going to say. That way, substorm onset is seen by the beating. The beating we know is a classical instability. I believe that's clear. And I'll say that we know it's in the near-Earth plasma sheet. And the streamers to onset scenario that Toshi and I have been talking about for quite a while now implies that the flow bursts in the tail, which carry the low entropy plasma, change the entropy gradient in the inner plasma sheet, and that's what leads to onset. But the onset is east-west aligned and it expands azimuthally, and that's due to the expansion in the east-west direction of the low entropy bubble. And the onset likely comes from flow channels that come from the day side over the polar cap into the auroral oval. So that's sort of my outline. So the definition of a substorm onset is that it's along an east-west oriented arc along the equatorial boundary of the auroral oval, right? That's the additional Akasofu definition, and we've seen it before. It's on the poleward edge of the proton precipitation, so we know it's sort of on the poleward edge of the partial ring current. So we know where it is in the inner magnetosphere. The onset always starts as beating. Can you see my cursor on the screen there? Yeah.
Yes.
Okay. So your little beads, the beads just gradually grow with time. They're just waves. Eventually they start to become nonlinear. When you get nonlinear, then you get all the action of the substorm expansion phase, and that's when the magnetometer drops and you get substorm current wedges and all that. The beating starts independent of that. And this has been seen for virtually all the cases that people have looked at. So this, I think, is just incontroversial. You're welcome to disagree with me, but I'd say it's incontroversial at this point. And that's what we need to understand, is this just a classic signature of an instability, right? The instability is east-west aligned, it's in the inner plasma sheet. I claim that we know this stuff. This is what we know. We shouldn't be arguing about it. You're welcome to disagree, but this is what I think we know and how we need to move forward. And I think the most major breakthrough we've had in the last little over a decade now is that by Toshi, that the pre-onset sequence starts with a poleward boundary intensification, which we know is flow coming in from the polar cap into the plasma sheet. It turns into a streamer. Streamer means they're adjacent flow, and it goes into the plasma sheet as one of our low entropy flow bursts, right? And that leads to the onset. And sometimes people say, I don't see a streamer, it doesn't contact the growth phase arc. But typically the streamers do not contact the growth phase arc. The streamers don't cause substorms. It's the flow, the low entropy flow channel in the plasma sheet that we see as a flow channel in the ionosphere adjacent to the streamer that brings a low entropy plasma in, and that's what leads to substorm onset. And it spreads azimuthally, it gets into the inner plasma sheet. And I'll mention that a little bit further. Earlier on, when we had hundreds of streamer observations leading to substorm onset, but let's see whether there's flows. And one of the early examples that we published was from the Pfizer radar. There's a substorm onset right here at this latitude, at this location, and you can see the flow bursts coming right into the time and location of the onset. We've now seen that with radar data for tens of cases. So I think, in my opinion, this is a little bit more controversial, but in my opinion, the flow leading to the onset and contacting the onset region with these low entropy bubbles is pretty clear. All right? Another kind of significant breakthrough, remember there's the beating, right? And the beating's just an instability. Is back when Bea was a graduate student, everybody looks at this as super darn in high time resolution mode where it's looking up along the magnetic meridian, and all this yellow color here is no flow, then all of us would look at this stuff here and say, of course, that's noise. But I don't know how she did it. But she said, look, if you average the flows over latitude, you get beautiful oscillation flows. Just a nice wave of very, very strong flows in the ionosphere. Poleward, equatorward, poleward, equatorward, poleward, equatorward. And then if you look at those and line them up on the auroral beads, equatorward, poleward, as the beads pass by. So the bead pass by, it goes one way, and bead passes by, it goes the other way. Here comes the next one, it's this way. Here comes the next one, it's that way. And it's oriented, so of course you get the converging electric field where the bead is, so you get the upward field line current. So this tells us important properties of the wave, its frequency and spatial scale of this wave, which is causing substorm onset. And then a little later on, Toshi was able to do conjunction with the beads at Themis orbit, and here's an example. And substorm onset you can see in the auroras right here. Then 2 or 3 minutes later, he sees all these waves, very similar wave characteristics to what Bea saw down in the ionosphere. So now we're seeing the features of the onset instability, in the plasma sheet. And while we didn't talk about that at the time, I think it's really critical, that when you start seeing these waves, which are the signature of the onset instability as seen in the plasma sheet, that's right at the onset of dipolarization. And you see the big jump and change in the plasma characteristics to the higher temperature, lower density, lower entropy plasma. So the onset instability, based on this one observation, is right at the boundary between the incoming low entropy flow channel, which is now spreading azimutally because we're into the inner plasma sheet, and the pre-existing plasma sheet. Right at that boundary, right at the entropy boundary. So it's right at that entropy boundary that you're seeing this onset instability. How it works and why that happens, that's for the future. There's a couple of nice papers on that. Okay, it's another example of a similar type situation by Sheng Chen in our group at UCLA. And by looking at and filtering the data, he can sort out the alphane waves that are shooting alphane wave energy to the ionosphere. And when he sees that on the Van Allen probe satellites or on Themis, it points right to the arc that's underneath it. So you know that when you see this, you're seeing the arc, and if you only have a simple situation underneath you, you know what arc that is, and this is just right during the beginning of a substorm expansion phase. So you see the alphane wave energy pointing to the arc. If you look at sort of the envelope of it, it gives electric fields that point in, so you got to have upward field line currents. And again, it's right at the dipolarization, right where you have the change in characteristics of the plasma. So you're going from the high entropy plasma to the new intruding low entropy plasma. So now we've seen that right at that boundary of the incoming flow channel twice. So that's something that really needs to get investigated more thoroughly. Now, another interesting point is sometimes these flow channels come in, or more often than not, they don't lead to onset. But what they do is give brightening of an arc along the equatorward boundary of the auroral oval, which would be like here. So the low entropy flow channel is coming in. It's obviously going to change the entropy gradient in the inner plasma sheet, but it doesn't lead the instability. It leads to the formation of the growth phase arc. So it kind of looks like it's the same process that leads to the growth phase arc as it leads to the substorm onset. But if it goes so far, it only leads to an arc. If it goes further, it leads to the substorm onset. It leads me to think that it might be possible to have a substorm onset without a growth phase arc, but I don't know whether that occurs or not. Okay, so the growth phase arc and the onset are both related to the new plasma intrusion with a flow burst that we see in the ionosphere, but we also see in the plasma sheet. So the front is a dipolarization, and then it's followed by the flow. You get more energetic, lower density, and lower plasma pressure plasma behind the dipolarization front. So it seems clear that the intrusion of the low entropy plasma is what leads to this instability. I mean, the situation is stable, okay? It's not a gradual change to instability, it's an abrupt change to instability. It's not like something just is blowing up and then marginally going unstable. Something has abruptly changed, okay? And the abrupt change seems to be the intrusion of that low entropy plasma. And as that plasma comes in, okay, I'll say that in a second, all right? So As you change that appropriately, you lead to the instability. And of course, what the condition is, I don't know. Now, the tail flows have a nice earthward component, right, in the plasma sheet, but the onset's east-west aligned. So none of what I said makes any sense unless you have something that's east-west aligned. And so you must consider what's east-west aligned. But of course, as the plasma comes into the near-Earth plasma sheet region where the substorm onset apparently occurs, that's where you get magnetic drift. That's the only thing I know that's east-west aligned and nicely east-west aligned. So the east-west alignment of the substorm onset's got to be related to magnetic drift. And you can see that very clearly in the Rice convection modeling of a bubble introduced at the tail outer boundary. And I'm thinking about the modeling of Che-Ping Wang back in 2018. So the flow burst comes in, and the electric field drift carries the low energy plasma off to the dawn side, okay? And then magnetic drift carries the higher energy ions off towards the dusk side, right? So that's creating an east-west aligned equatorward boundary of the bubble. And as it's doing that, if you look at the MHD equations, that's a divergence of the heat flux vector. So that process of spreading and making it east-west aligned is also growing the bubble, and it does so substantially. So it's helping develop the conditions that leads to instability, just that magnetic drift in the transition region as we get to the near-Earth plasma sheet. And he has specific predictions of what you should see with this. On the dawn side, you see a flow enhancement associated with the flow. It's in the region 1 field line currents that are within the bubble, and those currents are downwards, and that's what we call DAPS, downward auroral polarization streams. Jiang Liu made up that name with me. And then on the dusk side, it goes equatorward of the auroral oval into the region 2 downward currents, and that's the SAPS region, okay? And we've seen that several times. So here's an example. We can now, due to the breakthrough of Bill Bristow, to obtain two-dimensional flows from the superdarn radar using the divergence condition, we can do things that we could never have done before. And so here's a case where we have the auroral measurements, okay? And here's the two-dimensional superdarn flows. Before anything happens, you got some flows over here, equator of the aurora, those are the SAPs. Got some flows over on the dawn side, a little bit more poleward of the aurora. Those are the DAPs. Okay, so in comes one of these polar cap flow channels, presumably coming from the day side, but it comes in and it connects into enhanced flows over here on the dawn side, which are the DAPs, and also connects, and this is poleward of the aurora, these DAPs, because that's in the downward region 1 current region on the dawn side, and into the SAPS region, just equatorward of all the aurora on the dusk side. That's the SAPS region. And it continues going, excuse me, until the flows decrease, and then that SAPS-DAPS stuff goes away. And you can see the same thing for substorm onset using these two-dimensional flows. Here, if you look right at the substorm onset meridian, you see the flows coming in, and this is the time of onset, and that's right where the flows hit the poleward bound, the arc that breaks up just the time it breaks up. If you go over to the dawn side, you see these strong DAPS flows, and you can see they're just poleward of the poleward expanding aurora on the dawn side. Strong flows just after the onset flows are seen coming in at midnight. You go over to the SAP side, you see the same thing, but now it's equator of the aurora. And you can quantitatively see that and see that in the flows. Just for fun, I thought I would show one example, which is a sort of a variation of the streamers to onset scenario, which is here. We got a nice view of the whole auroral oval. Here's the auroral poleward boundary. This diffuse aurora in here is probably proton aurora. Some electron aurora going on in here. And pretty soon, You develop a nice, very well-defined arc along the auroral poleward boundary. There's got to be a polar cap flow channel adjacent to it. It moves equatorward, 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 and as it gets nearer the onset, boom, there it goes as it gets near the equatorward boundary of the auroral oval. And then, maybe I should play that again, starting from maybe here. So here it comes, here it comes, here it comes, here it comes, here it comes. So it's sort of tilted like a streamer, and there goes a substorm. And then the westward traveling surge comes, and it just climbs right to the west along that sort of tilted poleward boundary arc. So that polar cap plasma is just pouring in, creating the westward traveling surge. But again, this is still like a streamer leading to the onset, but it's the poleward boundary arc itself, and not like a separate streamer that came off of a PBI. So in conclusion, I think this is the scenario. It's the new intruding plasma from a bubble that forms or enhances the growth phase arc, or can lead to, eventually leads to onset. Okay? And the growth phase arc indicates that a previous bubble had changed the conditions leading to onset. And it's a classic instability that's east-west aligned because of the east-west orientation of the bubble in the region where magnetic drift takes over, okay? And that's a big change in the entry gradient right at the equatorward edge of the bubble, as we saw in those two examples. And then it spreads to the west and it spreads to the east, and the onset, if you look at the beating, it starts in a limited local time region and then spreads azimuthally. And that's just associated with the azimuthal spreading of the high energy ions of the bubble as they magnetic drift off to the west, expanding the bubble to the west, and the electric field drift of the lower energy ions as they drift off to the downside. And so this was an observational picture that Shasha observed back in 2009 before we had this flow channel, but now we add that flow channel to the picture. And another detail is that there can be multiple onsets. You can have an onset over here and then an onset over there. You don't have to have, they can be completely separate and sort of going on at the same time. And you start running the definition of what's a substorm onset and what's not a substorm onset. But they all start with beating. They all get followed by the nonlinear development. And so don't worry so much about the name calling as to whether it's an onset or an intensification or whatever it is. If it's got the beating and this kind of development, excuse me, it's the same physical process, and that's what we want to understand. So thank you.
Does anyone have any questions?
So I have one if there are none currently in the room.
Go ahead, Jason.
So yeah, this is like just a very broad question. I mean, like, a beautiful talk. Like, I broadly agree with what you're saying. I think it's like the right general picture, but you didn't mention reconnection very much. What role do you think reconnection plays in the onset, if any, besides just producing the flow bursts that map to streamers?
None.
Okay.
The instability is in the near-Earth plasma sheet, right? So in the onset instability, that's a plasma instability in the near-Earth plasma sheet. That's not reconnection. That's something else. Now, there's a lot of evidence that near-Earth reconnection starts soon after that. When you start seeing those streamers, the nonlinear development of the onset that occurs, it might be 30 seconds after onset, it might be 5 minutes after onset. That's when the reconnection is starting in the near-Earth plasma sheet and driving those really strong streamers and magnetic field perturbations that we see. So it's really important to the substorm process. It's just not the onset. It's sort of a post-onset, but critical to having the full substorm development that we know and love. But it's a consequence of the onset instability, which is this likely kinetic instability in the near-Earth plasma sheet. Thanks for allowing me to clarify that.
Oh, yeah. I mean, so I think I broadly agree, but I thought maybe there would be some dissenting opinions about that in particular in the room. Maybe that's not true and I'm just confused. If I could ask just one more very simple question, like, what is your explanation for which events become pseudo breakups as opposed to onsets? Is it a
Okay,
threshold or something?
that's a whole nother topic that I like to think about and I enjoy. The flow to onsets, which is coming in from the polar cap, seems to be what causes the flow burst to lead to onset. And from the few examples that we've looked at, it seems really clear that if you continue those flows, the expansion phase continues. If you turn those flows off, it stops. So sometimes you'll get flow that only lasts for 2 or 3 or 4 minutes. So the substorm doesn't know the difference. It starts to develop in its normal way, but then you lose the polar cap flows, and so you'll lose all the flow into the oval. So that shuts it off. So it's just related to the duration of the enhanced flow channels. They're impinging on the auroral poleward boundary, in my unproved opinion.
Very nice. Yeah, thank you so much.
So, Larry, I saw one of your slide that shows like initially there's a proton precipitation, and then after some time when substorm onset, then it become electron precipitation. Is that always the case?
Actually, probably yes. I mean, you don't know 100% sure the proton precipitation there, but when you see that diffuse aurora band precipitation, which covers 1 to 2 degrees of latitude in the equator boundary of the oval with no structure, that's almost certainly the proton precipitation from the outer portion of the partial ring current, or from the partial ring current, that's come in prior to that, that's charge exchanging and spreading. And then when people have looked at that, in the now relatively distant past, the substorm onset occurs on the poleward edge of that proton precipitation from the partial ring current. I guess that might be related to the magnetic drift effect. Maybe that's just my idea.
Okay. All right. Thanks.
Hello. You may have already explained this before. Since I arrived late, I want to ask this simple question. So, could you please explain why the reason for the eastward-westward expansion after the onset?
So the bubble is coming in. Let's just say it's going pure equatorward in the plasma sheet, right? And as it gets into the near Earth plasma sheet, the electric field carries it, sort of around the harangue reversal off towards the downside. But that's just the electric field drift. But as you get into the stronger magnetic field, the so-called transition region, you get magnetic drift. So the higher energy particles then drift off to the west. So the electric field drift is carrying the low energy particles one way, and the magnetic drift is carrying the higher energy particles the other way. So that low entry bubble is expanding azimuthally and growing precipitously at the same time. So it's that a combination of electric drift and magnetic drift, I think, is so critical to why it's east-west aligned.
On that note, actually, it seems to me that this argument is, because it's saying that the colder ions are drifting one way and the hotter ions drifting the other, but both of those are spreading this equatorial bubble. Shouldn't the bubble and the beating in the aurora look different depending on if it's east or west of sort of where the streamer comes in? Does that make sense?
Yeah, makes some sense. And interesting question. Yes. Yes, I think that's something that would be interesting to look at. And you would see that also in the radar data, right? If it's more to the east, going off towards the dawn south, you see it. And the simulations, Chaping's simulations actually show that. Most of the flow would be in the DAPS region on the dawn side. And if the bubble's way off towards the dusk side, it might just stay in the, it's really based on where it is relative to the dawn and dusk convection cells, if you will. So if it's on the dusk side, you should see mostly just saps. And so you might just see more saps than DAPS or more DAPS than saps. And then that would be related perhaps to the auroral manifestation as well. So that, yeah, I'd love to see somebody think about that. That's really good.
Okay, one more question.
While I agree with your drift picture in the magnetotail, the green auroras are caused by electrons, and the substorm current wedge and the westward traveling surge is electron precipitation, isn't it?
Yes. Yes, of course.
And how does this fit in your picture of the ions?
Well, that's the bubble that's creating the instability, right? And then you got to develop the converging electric fields to give you the aurora. And so like what we saw in the ionosphere, what Bea saw in the ionosphere, where she saw those very strong electric fields pointing into each bead, so that's where you got the upward field line current, so you get the electron precipitation. And of course, the growth phase arc is also electron precipitation, and that's caused also by the expansion of the bubble. There's a Young paper on that several years ago, which shows how that leads to a localized region, sort of elongated in the east-west direction of upward field line current on the edge of the proton aurora.
Okay, let's thank our speaker one more time. And Jesper.
Oh, I think I'm going to go on the Zoom, but yes, she told me how to do it, so hang on a second. Oh, okay.
Online people need to see his slides.
Yeah, HDMI is there, so, but yeah.
It's on. It's already on Zoom.
Doesn't he need the screen sharing? No. Okay.
Okay, so just go to the floor. Okay. Okay, excellent. Okay, thank you so much. And we just heard, thank you, Larry. Always enjoy your talk, so thank you so much. And you basically set the stage for me, so I appreciate it. And many of the questions that were related to the entire issue about viewing bursty bond flows, the wedgelets, as a fundamental building block from which everything is essentially comprised. So Shin and I have addressed that issue for years, and we actually have a mission flying. Our community have a mission right now flying with one of the two objectives is to resolve this issue of wedgelets versus large scale. I still like to show this movie. It's downloaded from Supermag. It's a classical substorm. It doesn't get much more classical than that. It's polar vis Earth camera superposed onto Earth, and then ground max from Supermag. And it basically shows you how a typical substorm starts, develops, and how it's evolved into the recovery phase. This is the picture we are dealing with. Now, you can have beliefs in this, that, and a third thing, but this is reality. And I do want to point out a couple of things. If you look at it, the individual vectors here in the bulge, notice you pick out one with your eye and see how it's behaving. It basically is coherent. It gets stronger and it wiggles a tiny bit, but it's coherent with the other vectors. It doesn't pop in and out over the period of this movie, right? So it basically enhances like the entire bulge here, and then you see it is essentially staying fairly stable throughout. So again, this is something we need to deal with. So, okay. So I have to talk about EASY because, of course, EASY is a super exciting mission at the moment. It's 3 small satellites that look down. It's a magnetic field mission that doesn't have a magnetometer. So wrap your head around that one. Essentially, the EASY spacecraft have the same instrument. They're completely identical. It was launched on March 15. They have 4 beams, essentially, look directions. Think of it as a 1-pixel camera in some sense. It measures the spectra of a line, and from that spectra, we can calculate what the vector magnetic field is at the emission altitude of some 85 kilometers. So we have the spacecraft coming by in a push-boom configuration. Each beam makes measurements every 2 seconds. So the first satellite makes measurements in this push-boom configuration. We do the inversions and get a current pattern for an equivalent current, the electrojet, And that gives us a sense of what is the structure. Now, the next spacecraft comes by somewhere between 2 and 10 minutes later. It also makes a map. And now we can see not only what is the structure, but how did it evolve in that 2 to 10 minutes. And the third comes by again, giving a third option of seeing how the system evolves. So, of course, everything we have here is carefully designed towards answering science objectives. And this is probably addressing exactly what Larry just spoke about. The entire view of everything is wedgelets versus it's a large-scale system. And the other one is the old classical substorm. You can say they're related, those two objectives, but we split them into two for multiple reasons. So if you look at just the substorm current wedge itself, going back to my own thesis, I could not squeeze in my results into the box of the McPherson substorm current wedge. McPherson is a big hero of mine, but I still could not make it work. So we came up with a different version, and here's 3 schematics here that we are trying to test with the mission. Okay, so for this, you may ask yourself, what on earth? Are you still talking about the substorm current wedge? And at the Jim CEDAR a few years ago, we invited Bob, and he actually had that question. But ever since he published his fantastic paper, there's just been a constant stream of new models. And in the proposal, we realized that of the thousands of papers that address this problem, you could pretty much organize them in 3 different groups of what the substorm current would look like. And they have similar characteristics. So we popped it into a schematics and said, where do these models differ? They differ in the question mark, right? So take a wild guess where easy is flying, right? Of course, we're sun-synchronous polar orbits, so we go straight through that question mark. That was the plan, at least. Then we got on a SpaceX Transporter 13, going up again March 15, and we were hoping we would be there, and this is actually where we are. This is 1 day of passes, so you get the wobble of the dipole and all that. So this is pretty representative. We're going to get that every day, over and over. So lo and behold, we hit it right on the nail, right? So we could not be happier. So that was good news. Now, the other questions is going back to, and that is what I'm going to talk about today, so essentially, which is what Larry just said. This is this concept of, it's a large-scale system. Here it's represented by Sergeyev and co-author's paper, but it could be any of the other large-scale patterns. Or versus it's a tiny bunch of tiny wedgelets. A side note, wedgelets actually was invented by Rostock, had a completely different meaning. It had little step-like moves of the surge. But it has evolved into this is now a wedgelet, so that's fine. I just have to give Rostock some credit there. He was the one that basically saw that with Kisabeth. So anyway, so this is the idea here, this is the way we saw it here. Images again from PolarVis, and if you see the one in the middle, it can be hard at these images, but that is a north-south streamer or a wedgelet, whatever you want to call it. And it has a lifetime of some 10 minutes-ish, and while the large scale on the left, there probably has somewhere between half an hour and an hour. So they differ in evolution, and they differ in scale size. So the difference between the spacecraft A, B, and C is, of course, carefully designed to differentiate between these 2 patterns. We cannot be 30 minutes apart because we can't see the evolution when it has a lifetime of 10 minutes or something like that. So that's why the spacecraft in between, the inter-spacecraft separation is somewhere between 2 and 10 minutes. At the moment, they're about 2:30 or 3 minutes, something like that. So we are now we are in phase E, and we are hitting it all the time. Okay, so it's designed to resolve this. I think we all know where it comes from to some extent, which is Global MHD. He is from Slav American and his Drive Center. It's a beautiful paper, and of course this is so appealing, right? You see these flow bursts, that red stuff there, and on each side you have a downward current and an upward current, so you form that flow burst forms a little wedgelet current, and in the ionosphere you have a little westward electrojet associated with that system. So you got a cause in the magnetosphere, and you got the effect in the ionosphere. It could not be more beautiful, right? The only issue is, does nature agree? And to what extent? I I don't think anybody disputes the presence of these or the existence of these. What the question mark here is, to what extent are these defining the westward electrojet or the big system? Is it just a perturbation on top, or is it actually a fundamental building block? So that is the question we are raising. Okay, so I have to remind everybody here about this old picture. So this actually is what we did, Shinutani and I. We wrote a paper a few years ago addressing this in a statistical sense. And what we did was essentially look at the old McPherson picture and say, okay, mid-latitude perturbation should be related to the aurora electrojet perturbation if it's a large-scale system, right? Because you have that's what essentially the left picture is showing, and the right picture is the mid-latitude perturbations. So the E components there, or west components on mid-latitude, as well as the aurora electrojet index should be correlated, if it's large-scale, that is. Okay, so let's just put that up in the corner and remember that for the rest of the talk. Okay, so here is, if it's a large-scale system, again, it's a global coherent system. The SML, or the Supermach version of AL, should represent the westward electrojet within that wedge. And it should be highly correlated with the feeding and drainage on each side of the system at mid-latitude. If it's, on the other hand, a bunch of little wedgelets that pop in and out, somewhat sporadically, and they're much shorter lived, then the SML will be represented by one of these wedgelets. That's the definition of SML. It's one station. It's not a global index. It's defined by one single station. And that correlation should be low, because the perturbation at mid-latitude is not really sensitive to the individual wedgelets, only partially. It depends upon the location and so on. Okay, so that's the background. So here's the approach we used. Here's an example here. We took Victoria and Brorfelde, actually in Denmark. So I can't believe, but that's the station we picked. And Victoria on each side, they're about 10 hours apart. And you see here Victoria, it's a little bit busy, the plot, but what I want you to look at are the two red curves there. It's SML in dashed, and the red solid curve is Victoria, the E component. And look how incredibly highly correlated they are. So it shows basically that whatever SML is doing here in the middle, and whatever Victoria is seeing over by the flank here off to the side, it's essentially seeing the same. It's highly correlated. Please notice that the axis for Victoria is inverted, so it's negative at the top. Okay, we can go to the other side, and we see something essentially identical, but now we flip the axis, because of course the east component has flipped, because we're feeding instead of draining the current in the middle. So what have we done here? We have seen that SML, the aurora electrojet index in the middle, is incredibly highly correlated with the base on each side. Okay, so we can do this statistically. So we picked about almost 10,000 events using we developed a new method to identify substorm onsets, and it had the target of being very careful with the timing and location. It's not all-inclusive, but it's very careful in terms of finding really reliable onsets. So anyway, we used 10,000 of those, and if you look at the plots here, this is Victoria on the left column, and Brorfelde on the right column. It's N at the top, and it's east at the bottom. And what you find here is that it centers, the N component is best, it centers somewhere around 23, just pre-midnight. And essentially here we have MLT at the bottom. So all 10,000, we just let Brorfelde and Victoria drift around, and then for each of the onsets, and then we plotted the perturbation as a function of MLT for this mid-latitude. And you see how consistent the pattern is. The solid lines, they are median and one standard deviation. We can also look at the correlation between SML and each of these stations. And you'll see suddenly it's incredibly highly correlated. Of course, it's anti-correlated at certain local times, but it's highly correlated nevertheless. And you can see that for both stations in both components. So we get a very, very consistent picture between the aurora electrojet measure used from SML, as well as these mid-latitude stations. It's just repeated over and over. Okay, we can focus more on that. and just look at Victoria here. Again, it's positive somewhere between 9 and 3 o'clock. It peaks around 23, the N component. Again, it's highly correlated. There's perhaps one thing I should have said here. If you look here, the perturbation in the pre-midnight is bigger in pre-midnight than it is post-midnight. I think that's an old, well-established fact that the drainage in pre-midnight associated with the substorm current wedge and the surge head is very focused and it's intense, while the feeding post-midnight is more distributed, and that shows up in these perturbations here. Okay, so again, we did the statistical study, and again, we find these very high correlations. So, okay, another study addressing somewhat of the same is a student, again, that used this network analysis with Sandra Chapman. And Lauren here, she did a fantastic job and published it in what is it called, Nature Communication, yeah. And the conclusion here, let me just bring up the conclusion, is that analysis from 41 substorms exhibit robust structural change from many small uncorrelated current systems before substorm onset to a large spatially extended coherent system approximately 10 minutes after onset. We interpret this as a strong indication that the Aurora electric system during substorm expansion is inherently a large-scale phenomenon, is not solely due to many mesoscale. And again, this analysis essentially treats all the magnetometers. It's kind of cool, actually. It treats them as independent stations and do essentially a cross correlation. So it's this network analysis, and you can see in the pictures here that it ends up with the green stuff, large coherent systems. So, okay. So let me go back, because we live at a time where theory is good and basic research is good, but it needs to be societal impact. We all live in space weather reality here. So we could ask, why does this even matter in terms of society? And it's perhaps important to just keep that in mind. So if we take these two standard pictures here, what we did for the proposal for our EASY mission was that we again compared that to two waterfalls. So in the left one, the large scale, the energy is being transported from the plasma sheet down to the ionosphere. In the right one, it also is being transported, same amount of energy or same amount of water. No difference, but the way it's being transported and deposited is very different. In the left one, you see a large structured, fairly steady system. In the right one, you have sporadic and structured system. The impact on our society, anywhere from communication to you name it, is very induced currents, is very, very different. And I guess I just want to emphasize to everybody, keep in mind today when you do something, never to miss that link to society. That's the reality we live in. So thank you very much.
Any questions?
So even if the dipolarizing flux bundles aren't kind of making all these individual wedgelet systems, they're still contributing to the, like, they're transporting magnetic flux, right? So they're still building up the substorm current wedge? It's just...
So I think that wording is where we perhaps disagree.
Okay.
The way we see it is that they certainly have a role in the system, as you described, but they are not a fundamental building block. They are perturbation on top of a large-scale system.
Okay, thank you.
I know Larry probably is about to yell at me, so, but that's fine. Again, we are not disputing the fact that they're there. We're not disputing that they're playing a role, but we are saying that there is a large-scale current system. So, yep, Larry?
Yeah, so I would say that, of course, you're not talking about option 3, which is that as we talk about that azimuthal expansion of the bubble, right? So the localized perturbation due to the localized current wedge expands azimuthally, and you can see it really clearly in Chaping's model over the course of 10 or 20 minutes into the large-scale system. So it could still be the fundamental building blocks are the localized flow channels, which I believe they are, but they evolve naturally into your large-scale picture over the kind of time scales that you're seeing it. So I think with your wonderfully timed set of spacecraft, that's my prediction for what you will see.
Okay. Okay, a couple of things, of course, is to some extent, I came from the Niels Bohr Institute, so we always like to trace things, right? Energy is a good way. So one of the things is, if these are the fundamental building blocks, do they provide the energy flow that we see deposited in the ionosphere? I don't think so.
You end up with a large-scale current system, right? And that's going to have the majority of the energy flow.
So again, if you just sum up how much energy is being transported by a bursty bulk flow, it's not sufficient. It cannot account for what we see is being deposited. So I'm just putting a different spin on it here, a different view of the problem, right?
Yeah, that's sort of my statement too, in a way.
Okay.
Could I interject with a question quick?
Yep.
Yeah, so I guess what I'm wondering is, does the global wedge versus wedgelets, debate here shed some sort of light on onset mechanisms, and if so, how?
Okay, excellent point. Of course, I thought about it and I read carefully your invitation, and I'm very grateful for it. This is the spin we took on it, and the issue, that's a very good point. The issue is sort of related to Larry's talk, as you saw. Larry said that, and I hope I don't put word into your mouth here, that reconnection is not the driver. We feel it is, and there is a localized onset for that, and it spreads out, and you get, again, the large-scale current system. So I think these indications of whether it's a wedgelet and it's a bunch of little forms, or if it's a large-scale system, I think that can be traced straight back to the mechanism starting it. So I think this provides some constraints here. Now, Larry, he explained in terms of a pseudo-onset versus a real onset, and that's a whole other question that I'm not sure that I agree with either. So yeah, I don't know if that answered the question to you.
Yeah, mostly. If I could just clarify one more aspect of it. I mean, it seems like there is a localized instability develops, and then once you've got enough energy injection, you set up a substorm onset. Does that necessarily entail the buildup of the current wedge, or is there some gap there?
So I'm not sure I get the question, and I'm not sure I have a good answer, but let me try, and then you can correct me. So the difference between a pseudo-onset and a real onset, so to speak, may very well be in the evolution, not the start. And to that extent, I think Larry and I agree. For whatever reason, the plasma sheet is not ready to really go large scale. I'm not sure why that is necessarily. But going back to your question, I think, again, it starts somewhere and somehow it spreads in the plasma sheets and becomes a large-scale system, right, in the classical picture. So again, I do believe that whatever the evolution is and what the building blocks are, you can trace that to the onset, back to the onset and the mechanisms. Yeah, I have a very hard time with the right one seeing how the plasma sheet does that, and for that matter, how the ionospheric signature of those is in line with what we see. So, I don't know if that answers your question, but it's a good question. So.
Yeah, I think it mostly does. It's hard to reconcile the localized beating onset picture with the global current wedge. I'm still just struggling over what the connection is there.
Well, even a large-scale current system has to start somewhere and then develop. We know, we have observations in the ionosphere that we know it starts somewhere in the oval. We see the onset. I don't think anybody disputes that. And then it spreads from that. So the question is really more of what is governing that spreading and that going from small scale to large scale, where we say it is a large-scale disruption of the plasma sheet. where I think Larry and others say, no, 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 it's just a subsequent number of wedgelets. So I hope, again, I don't put words in your mouth, Larry, and everybody, so I think that is where the difference is.
Okay, yeah, that was very illuminating. Thank you.
Were there any other questions, or should we go to the next talk? Okay, let's thank our speaker one more time.
Thank you again.
Oh, so I'm not going to be on Zoom?
So he can project this without Zoom. So
Okay. Do you have any sound on your presentation? No.
so if you make a PowerPoint full screen, but now this is on a different desktop. This.
Oh. Apparently not. Where is my mouse?
Yeah, the mouse is over there. Well, it was there. And now it's right here.
Let's try to get it there. I can't see. Oh, it's here.
You can close
Is it on this side? Yeah.
Okay.
Oh, the Zoom doesn't matter.
Yeah, I guess it was.
Yeah. Looks good online.
Okay, we got that squared away. So I'm going to switch gears in two ways. First of all, I'm going to take a little bit more global look and look at the system as a whole. And rather than having answers, I'm going to present more questions and puzzles that we have. So what I'd like to talk about is the substorm onset problem. And one of the things that we haven't really done is to talk about what is a substorm. And that's where I started when I started thinking about this talk. I started thinking, what is a substorm? And I found this a very nice paper by Dan Baker a couple of years ago, published in Frontiers, where he talked about substorms as these irreversible energy cycling processes that distribute energy drawn by the solar wind into the magnetosphere-ionosphere system. And then the obvious question is, what is the focus of this? What sets out that global instability? Substorms have also been described as nonlinear instabilities. They've been modeled by nonlinear models like a drippy faucet or a sand pile dripping sand when you add it to the top of the pile. And there the question is that you see these periodic unloading events, and the question is what sets up the periodicity in the system, and that's another question that I will be examining. And the third point that we often like to talk about when we talk about the significance of our field is that we say, well, substorms are ubiquitous in the universe, everywhere where there's plasma, where there's acceleration of particles, there's substorm-like features, and I'd like to challenge that view in a little bit at the end. So this is the traditional picture where we start. Magnetic reconnection, we all know about the Dungy cycle, the reconnecting convecting magnetosphere, where reconnection is this process that breaks magnetic connectivity between regions and also converts magnetic energy to plasma kinetic energy. And that's the way that the magnetosphere cycles solar wind energy through the system. And this picture was made more dynamic than by Ed Hones, talking about the substorm cycle really as a creation of a new X-line in the middle of the magnetosphere, and the explosive release of the magnetic energy into plasma energy that led to plasma acceleration, plasmoid ejection out of the tail, and particle precipitation into the ionosphere. And then you have conversion of the magnetic energy into plasma energy in the magnetotail, and you have the loading-unloading cycle where the variability really comes from the onset variability in where and when and how the tail reconnection happens in the magnetotail. So if you look at the energy conversion process, MHD simulations are a great tool for doing that, because rather than having one point measurement in a very big system, you have a complete understanding of the system within the limits of the MHD description, of course. And what you see, if you look at the graphs that you see, are looking at the magnetosphere from the sunward side. So the projection of the dayside magnetopause shown in blue, and the heads of the tail lobes in red colors. And the red colors indicate energy conversion from thermal to magnetic, so creation of magnetic energy, which we see as the solar wind energy gets into the system, it gets stored as magnetic energy. And in the dayside, due to the dayside reconnection process, you're destroying magnetic energy and creating thermal energy. And so that's very consistent with the Dungy cycle. And where exactly those regions are depends on the IMF orientation, with the large-scale X-line, which is the black line there, moves as the IMF-BY tilts the sort of the equatorial plane in the solar wind magnetosphere interaction. And if you look at the energy transport in the system, and this would be a video if I could find my mouse and get it going, since it doesn't start automatically. You can see the energy input and the great variability of the energy input in the system as the solar wind drives, and you can see the energy going into the magnetosphere through the tail lobes, and you can see energy flowing out as a consequence of the dayside reconnection from the dayside. And this is a very repeatable pattern, and again, very consistent with the Dungy picture. So we've talked already and heard a lot about flow bursts, and this is a picture I took from Mike Henderson, looking at or arguing that if there is an X-line somewhere down the tail, you have flow bursts in different sizes, and the most efficient ones that are carrying energy and connecting to the ionosphere are sort of mid-scale, these 1 to 3 RE scale size bubbles that are sort of just in the right scale size that they can get transported relatively close to the Earth, and then they, as those field line currents map to the ionosphere, those are the ones that you see as streamers or torches or poleward auroral arcs, as Larry showed. And you can see those traveling as the bubble travels from tailward direction towards the Earth in the ionosphere. That corresponds to something traveling from the poleward distance towards the equatorward part of the oval. Again, very nice picture. And here's just a statistical association of Reconnection events, a list produced by Nagai in a recent paper, some 700 or so reconnection events. If you take the solar wind energy input, you can see that reconnection events are preceded by enhanced energy input. This is the epsilon parameter on the top graph. The bottom graph shows the AL index, and you can see that reconnection typically is associated with substorm-like AL enhancement in the tail. Okay, so very consistent picture that reconnection in the magnetotail creates auroral activity, creates all of this, the AL signature that we associate with substorms. And if you look at simulations, this is Austin Brenner's work. You can see the formation of the plasmoids on the field line picture, and in this one, you're looking down at the equatorial surface of the magnetotail, and you can see the flow bursts in red color moving towards the Earth. So you see these mesoscale flow channels that are generated as a consequence of reconnection in the magnetotail. So again, simulations, observations, all in very nice agreement. But the damned auroras that spoil the whole fun because they just don't fit in the picture. As talked by Larry and by Jesper, the auroral substorm does not start from the poleward edge, it starts from the equatorward edge. It doesn't expand from poleward equatorward, it expands from equatorward towards the pole, and it expands east-west. And none of this is very well explained by anything that I showed above. So, what can we do? This, of course, has been linked, the auroral expansion has been linked to the substorm current wedge, and I don't need to say much. You just heard Jesper's talk on how this is a coherent current system that maps to somewhere relatively close to geosynchronous orbit, definitely not as far as the reconnection region in the magnetotail. How do we know that? We can infer it from geosynchronous in situ observations looking at the field dipolarization, and we can also look at the auroral precipitation and see that the onset arc often sits right on top of the diffuse aurora that we know maps to very dipole-like field lines. Here's just a schematic of the problematics put together by Emma Spansvik and Eric Donovan already quite a while back. So it just points out that the discrete aurora and diffuse aurora and the onset arc map to the inner magnetosphere. The X-line is in the magnetotail. And here's the red figures show one of my early mappings of the auroral onset into the magnetotail, showing that the onset region, onset auroras map to roughly inside of 10 Earth radii or so. And the right-hand side statistics is the 700 or so reconnection or tailward flow events identified by Nagai, which would be the reconnection signatures of substorms. And if you look at these, you clearly see that there's a very clear distinction of where reconnection occurs and where the auroral substorm is. So we really need to, before we can start to talk about the onset mechanism, we also need to talk about what connects these two signatures of the onset. So there's been several attempt to connect these two processes. This has been a long-standing problem. Larry and Toshi have been talking about the streamers coming and activating as the arc reaches the equatorward arc, as the streamer reaches the equatorward arc, it activates the substorm onset. Well, maybe, but it certainly may happen and has been shown to happen, but it certainly doesn't happen every time. So what about the other onsets? Then the question still is in my mind open, what is the inner magnetotail instability? Why some onsets have these flow channels and others don't? So while it may be a partial explanation, it certainly is not a full explanation. There's also been work looking at the inner magnetosphere instability and looking at the drift shell splitting that might lead to a pressure anisotropy in the inner magnetotail, which would lead to a ballooning instability that would then drive the inner tail unstable and allow creation of the substorm current wedge. That leaves the open questions of what causes the simultaneity, because we know that reconnection happens in very close association to substorm onsets. So what is the association of the reconnection that happens and this ballooning instability? So again, maybe partially a solution, but not the full picture. Minna Palmroth put together this ion kinetic simulation and showed that as that goes, this is a very complex simulation, but look at the center of the magnetotail that creates a large-scale fold. As that fold develops, it leads to a drift instability in the inner part of the magnetotail that connects to the reconnection region and then leads to a plasmoid formation. That is the first thing that I've seen that really connects the two instabilities, one kinetic instability in the inner magnetosphere and reconnection in the magnetotail. But it does leave open the westward and eastward expansion during the onset that you don't really see. Maybe this simulation isn't run long enough, or maybe it's not here. And also, this simulation does not have an ionosphere, so the feeder line currents are not there. The substorm current wedge is not, and certainly the contribution of the ionospheric processes is not part of this picture. So again, maybe one piece of the puzzle is here and points to the importance of the kinetic processes, not only in launching reconnection, but also launching the inner tail instability. All right, so what about the substorm periodicity? So this has been talked about as a nonlinear system that you can look at like a drippy faucet or mass on a spring where you add mass and lose mass when the spring gets stretched enough. And these systems do lead to periodic activity in the magnetotail. If you look at the observed periodicities, there's a wide variety depending on how you define your substorm onsets. You can get single bump distributions with relatively small periodicities or wait times less than an hour or so, or you can get multimodal double-peaked structures with a shorter, less than an hour, and another one maybe between 2 and 3 hours wait times. There's been a couple of modeling attempts. The Faraday loop model was done already in the 90s. It took some tail characteristic parameters and came up with something like 2.5-hour periodicities. Steve Morley and Mervyn Freeman did another one that they call a minimal substorm model, just using arguments of energy input into the magnetotail and that being released when the tail reaches a critical state, and they got a 2.7-hour time series. So these seem to produce something that's in the same ballpark as observations. So, but it still doesn't answer when and where does the next substorm occur. And if we want to understand the onset, you do want to understand not only where and why, but also when does it occur. And so in the next, I'll look at a couple of different options that there might be. Triggering, so solar wind, rapid changes in the solar wind are sometimes associated and statistically are associated with substorm onsets, but certainly there are events where there's absolutely no trigger in the solar wind. So may contribute to the wait times, but is not the answer to everything. Growth phase energy input, so this is the growth phase scenario where you load the system until sufficient energy to power a substorm has been loaded. The left figure here shows an average substorm growth phase energy input, which is of the order of 0.2 petajoules, just assuming a standard 90-minute growth phase. And here's a steady convection event where there's no substorm for several hours, and the energy input during that time is 2 orders of magnitude more. So again, there clearly are periods when you can load energy into the system without it going unstable. Is there a critical energy state like Morley and Freeman were saying? This is simulations by Austin Brenner. This is a steady solar wind driving, and what you're looking at, the top panel shows the tail energy content. So that's the energy state of the magnetotail integrated magnetic and plasma energy together. Clearly, there are energy releases without it always reaching the same maximum state. So no, there isn't an obvious energy state that would lead to energy release. Similarly, there's no obvious trigger when the solar wind changes, and there's no obvious. The one thing to notice is that even though the solar wind driver is absolutely steady in between the intervals, the energy input is variable throughout the intervals. So the magnetosphere has a way of choosing how much energy it actually accepts any given time. Rate of energy input, so if you drive the system higher, reconnection moves closer to the Earth, the wait times become shorter, but again, that doesn't mean that reconnection would come all the way to the geosynchronous orbit or even close by into the transition region. And again, if you compare sawtooth events and substorms, you see the reconnection moving closer due to the higher driving. You move the dipolarization closer, you shorten the wait times. But again, there's no real indication of what would happen. And lastly, just looking at the tail reconnection and substorm onset association. So I took 3 different lists of substorm onsets and compared those with the reconnection list. And yes, it peaks at the reconnection time. So obviously, a portion of the events, onsets are associated with reconnection, but there's lots of reconnection that happens outside of substorm onset times. So reconnection alone is not sufficient for substorm onset to occur. And since the chair is standing up, I'm just going to leave my conclusions and take any questions that you may have. Thank you.
Thank you. Any questions?
Hey, at the very beginning, you mentioned like sand pile collapse models as one of the ways that these were modeled. I know that certain sand pile collapses are given as like classic examples of critical phase transitions or like self-organizing criticality. Have people looked at substorm onset in that way?
Yep, there's a whole body of literature from 1990s and early 2000s that looked at both the self-organization and the criticality, and to the best of my understanding, that didn't really help us understand the substorm process any further.
Cool, thank you.
It certainly is not a low-dimensional system, which would have helped a lot if it were.
Okay, yeah, thanks. So actually going back to the self-organized criticality, there were these papers, a bunch of papers, as you know, to you, that basically it's very straight, caused many scale sizes or orders of magnitude. But there was another paper by Tony Louis who said there is a bump where the substorm occurs. And so there was some dispute about what those distributions look like. And so I think it's an excellent question. So one question for you, Tuija. Pat Newell and I did for the Newell substorm list and ours, we did look at the wait time. And we submitted the paper and said, this is pancake flat, so it's a Poisson process. It's very nicely organized. And we had a fantastic referee who said, wait a second, I think you're plotting it wrong. And he was right. So we plotted it slightly different and saw that it was indeed scaleless, above 3 hours, but then there was a different slope for less than 3 hours. So we basically saw that as there's 2 modes of the systems. It's a Poisson process for longer, but for shorter, it really is not. So there's something with recurrent substorms that behave slightly different from isolated substorms. So I'm not sure you have a comment to that. Do you have any idea why that was? You keep getting the same 3 hour-ish all over the place, if you notice. There's something in the system there, right?
There's something in the system there. What is it?
I'm not sure.
Is just so elusive.
Yeah.
I tend to think that the sort of the 20 to 30 minute time scale is not a substorm time scale. It's too short. Substorms are longer than that. But on the other hand, that is sort of the time scale of pseudo breakups. So it may be some, I don't know. But I would definitely say that to get a substorm, by which I mean that you get the global substorm current wedge and the global reconfiguration of the magnetotail and a plasmoid release, you can't get that under most circumstances in a time scale of 30 minutes.
Okay, and I'm glad we have the same definition of a substorm. So thanks for saying those words. Thank you.
Okay, time for one more question.
Well, I'd just like to comment on that same question. You were talking about when things happen too close together, we tend not to call them separate substorms. There's also a selection bias that the longer it has been since something substantial has happened, the smaller a perturbation we look for to call it a substorm. So I think there is some selection. You can find times that are quiet for 24 hours, but then anything that happens, we call that a substorm now. Whereas if it had happened in a period of more activity, we would have said, no, 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 that's not a substorm.
Okay, let's thank our speaker.
I need an adapter. Okay. There should be a white adapter. I'll go get one. I'll be right back.
Someone else. Yeah, so he needs to stop sharing the screen, so wait for a moment. He will come back with a connector.
Any sound on your presentation? No. Okay. Close Zoom.
Yeah, just go with this. Oops. Okay, here we go.
Good. Thank you very much, Tosh. Thank you. Oh, thank you for this opportunity to talk. I'm afraid I will again change gears because I will discuss plasma theory related to substorms. Interestingly, it was barely mentioned, and also some I would say theory-based data analysis, which is called data mining. Before I start, I would like to thank Harry Arnold, Grant Stevens, Titsu Matoba, Anton Artemyev, Kolya Tsiganenko, Slava Merkin, Mark Sisdak, Natasha Vazulko, and many others who contributed to this summary. Let me start from another Greek word, dilemma rather than dichotomy. You know that among the great archipelago of substorm models, there are two big islands. One is called Near Earth Neutral Line model, which the previous speaker definitely lives in. And another is current disruption model. In the first model, people claim that the substorm starts from reconnection somewhere in the tail, and then something happens in the Near Earth region. Other authors claim that something happens in the Near Earth region, and the signal then propagates tailward as a rarefaction wave or something like that. There are arguments pro and contra, but I will discuss largely the plasma physics implications for these theories and other things. So the the theoretical roots for the first concept was the Tiering instability theory published by Coppi et al. In 1966. They just explained that thin current sheets which are spread in a tail, if they are thin enough and long enough, they have a tendency to bunch currents because parallel currents attract each other, and they form these bunches of closed field lines with X lines in between and reconnection. And this is what powers substorm onsets. In an alternative view, supported by largely Tony Louis, who recently retired, and many other actually theoreticians, non-reconnection plasma physics models were involved to describe this reconnection in the Near Earth region. They may be driven by current, like current-driven instabilities of Tony Louis, or driven by buoyancy, people already discussed with instabilities driven by entropy gradients. Let me report a little bit on the progress in the first scenario in the tearing instability. It was a very dramatic period when, after many attempts to describe tearing instability in the presence of BZ component, our colleagues Lamberge and Pella arrived at the conclusion that the tearing stability extends from global to microscales. On microscales, you can destabilize a current sheet only if you demagnetize electrons. Sorry. On the other end, on the global end, you actually cannot demagnetize electrons because for configurations with constant BZ along the tail, the corresponding mismatch coefficient, CD here, is equal to 1, and the stability condition essentially reduces to the condition of WKB approximation. So the wavelength should be less than the inhomogeneity scale. There was no way to destabilize the system if electrons are magnetized. So more recently, we have found with Karl Schindler that there's still a way to destabilize ion tearing mode if your configuration has a tailward gradient, region of accumulated magnetic flux. Let me just show you this animation. The color here is the reconnection electric field, out-of-plane electric field. As you can see, after some initial perturbations, the system develops very interesting instability, not very similar to conventional plots of current bunching, which I showed from Copy et al. You can see that the region of accumulated magnetic flux starts moving upward, and as you can see, it becomes steeper. Essentially, as you can see, the first effect of the tearing instability is not a change of topology, but the formation of dipolarization fronts, regions of even sharper magnetic field gradients. So this is the development. So interestingly, this dipolarization front formation helps explain current disruption, which Tony likes so much. What actually Tony Louis made, he took our 3D peak simulations of dipolarization fronts and interpreted them as a current disruption phenomenon. As you can see, similar to the current disruption theory, the current in the bottom left panel increases and then rapidly decreases, while the BZ component increases as it should be in the current disruption theory. And you can see here that the current becomes filamented. It's a typical configuration when then the dipolarization front arrives at the inner magnetosphere. What is still first? Buoyancy-driven instabilities or tearing instabilities. It's still a not solved question. Recently, Slava Merkin developed very extensive theory of this stability, of both instabilities. I try to highlight here the corresponding threshold, and there is a plot which shows some comparison. Not to complicate this theory, let me just summarize. Interchange and ion tearing stability thresholds are similar. In particular, equilibria with the Taylor BZ gradient are both tearing and interchange unstable. Moreover, for models investigated so far, the interchange modes have lower thresholds. At the same time, in simulations, they are not necessarily dominating. We often see that the flux accumulation regions first propagate tailward and interchange instabilities develop on top of these perturbations. Now, remaining problems in theory, we still do not know what provides the onset of reconnection? Is it the ion tearing instability, which occurs due to demagnetization of ions? Or it is the electron tearing instability, which appears when you squeeze the current sheet to demagnetize electrons? Moreover, we do not know why in simulations, X lines appear so close to the left box. Let me just summarize all these problems. In case of electron tearing instability, we definitely need to drive our system to squeeze the current sheet. Whereas in case of the ion tearing instability, we need to create this region of accumulated flux. However, we do not know, is the onset driven or spontaneous? So what is the role of driving? And we do not know how the ion scaling current sheets may appear when they are absorbed, so beyond 20 RE in the tail. And what are their stability properties, if they exist there? We do not know if flux accumulation regions form prior to substorm onset, and we do not know what is the mechanism of their formation. Finally, we do not know, again, previous speakers partially discussed this topic, what are the mechanisms of instability? In particular, why configurations with BZ humps are not destroyed by ballooning or interchange instabilities. Theory only partially answers this question. And to answer them, we try to use another type of data analysis, which is called data mining. Data mining uses the property of which we already discussed here, that substorms are recurring. So we have roughly one substorm every few hours. So using this property, we can consider, we can fill the space of observations, very rare observations. We have barely a dozen of probes at the same time. But we can use historical data and put them all in this multidimensional space. As you can see, it is formed here by the SML index, its time derivative, SMR index and its time derivative, and solar wind VBZ parameter. It is important, and this is why I call it sort of theory-based data analysis, that we use time derivatives of indices. To understand why, it just helps you understand the trends. For example, if you know the coordinate of the pendulum, you cannot predict its evolution. But if you know its velocity, you can already trace its evolution. So the hope is that we consider our system in this space, the whole data which we have, magnetic field data, and consider only a small part of this system. We can trace the evolution of the system. It works. We discovered that then we can describe the stretching and depolarization of the tail current sheet. Moreover, here I show you an example when we took two magnetic field configurations. Here I just show the BZ magnetic field in a meridional plane and subtract one snapshot, one configuration from another. So here is the variation of the BZ field during the substorm onset. As you can see, closer to the Earth, you have very strong variations of BZ, meaning that you have strong electric field and very unsteady reconnection. Whereas farther in the tail, the perturbations are weaker, so one can expect that you have steady reconnection there. Surprisingly, you can see here in the bottom panels, it is consistent with peak simulations of similar equilibrium. So data mining suggests that the near-Earth reconnection is spontaneous, which is more consistent with the ion tearing models, while the more distant tail reconnection is driven, steady, and most likely associated with the electron tearing instability. Just a few words about this finding the proper location of the X-lines. As you know, in statistics, which here shown by Nagai, the X-lines appear largely beyond 20 RE in the tail. So it is important, it is necessary to explain how thin current sheet may exist in a distance from 10 to 20 RE. If their thickness is just comparable to the ion gyro radius, it cannot be explained by the isotropic magnetic field, isotropic current sheet models. Moreover, as was recently shown by Artemiev and colleagues, the electron anisotropy cannot describe stretching of the tail. We recently developed a generalization of the Harris theory. You can see here the highlighted frame of the standard Harris solution for the current sheet. We recently developed a generalization of the Harris theory taking into account ion anisotropy. And it looks like it does explain the extension of thin current sheets beyond the isotropic approximation. And as you can see from the top panels here, which show for isotropic equilibria, magnetic field lines strongly follow the isocontours of the current density. However, here you can see that current density isocontours are stretched much more than the magnetic field lines. That's why we call them overstretched. Interestingly, overstretched current sheets definitely solve this problem of the close location of the X-line to this left boundary, near-Earth boundary of the simulation region. As you can see from this panel D here, we can now see the X-line formation at 70 ion inertial lengths from the left boundary. Moreover, we see here, I hope to discuss it briefly in the next session, the onset starts not from the change of topology. The onset, as you can see here in the bottom panels, which show the difference between velocity in the system and average velocity over the whole simulation box. They show that a reconnection onset starts from a spontaneous generation of divergent flows. Divergent flows. Near Earth ions and electrons move faster towards the Earth than farther from the Earth. And this motion tears out the current sheet. So in other words, it explains why in the tail, it is not the change of topology, but the process inherent to tearing instability, mutual attraction of parallel current filaments, drives this system. Let me just stop here. I hope I will discuss it later more. BZ humps, do they appear in the tail? Yes. Our data mining reconstructions show that BZ humps appear in many instances of substorm. They precede the reconnection onset. But is it the whole story? The answer is no. Let me note that so far, everybody discussed substorms in a tail. I'm sorry. So far, we discussed the substorms within a very specific region, 31 RE. This is the region which was available for most of the missions, except Artemis. And now we used Artemis data to reconstruct the magnetosphere till a lunar orbit. We already discussed, TUIF in particular showed this nice Danji cycle. But what is the real configuration of the tail, and if there is anything interesting beyond 31 RE which is related to substorms? I assure you that there are many interesting things there. You already see it here, actually here. The open-closed boundary typically located The open-closed boundary is typically located at 40-45 RE. And effort of this boundary, we observe a region of significant increase of the magnetic flux. there is indeed an accumulation of magnetic flux, but it largely it is beyond 30 RE. So this is a classical picture which we all discussed so far in the absence of Artemis data. So we see thinning of the current sheet, reduction of BZ, maybe some increase and formation of the hump around 20 RE. And during the expansion phase, you see the dipolarization. Look what happens if we take into account the outer part of the tail till the lunar orbit. You will see that there is also accumulation of flux between 30 and 40 RE. And after the onset, something happens with this accumulated flux. Apparently, it is redistributed partially to the near-Earth region and partially farther from the Earth. Just to mention, to confirm that there may be important aspects of the substorm evolution beyond 31 RE. And the last point of my presentation. I started from this dilemma, which Vasilis Angelopoulos and colleagues tried to solve with the famous observations. And in the original paper, if you remember, the X-line was just an artist rendition. The models of that generation were not able to resolve the X-line formation in the tail. So the conclusion about the X-line was just made on the basis of 2 probe observations. Now the data mining reconstruction allows us to draw this X-line. You can see it here. And it is now confirmed by, not statistics, I do not know how to properly call data mining, partially statistics, but it is, this image was driven using 26,000 effective probes in the magnetosphere. Moreover, this, as was noticed before, the event which was considered in that seminal science paper by Angelopoulos was only the second of these events. And there was another activation an hour before. We considered both events. And what we have discovered, surprisingly, Tony Louis was also right. Before here, this panel F shows, orange light shows the evolution of the thin current sheet during these events. And as you can see, before the activation, which was published in the science paper, there was an interesting behavior of the thin current sheet. You can see it in this panel B. The current sheet increased and then rapidly dropped. So the whole sequence of events consisted of 2 activations associated with substorms, small substorms, and a current disruption event in between. If you, by the way, if you check another interesting feature here, if we take magnetic field distributions and subtract one snapshot from another, so in other words, these plots show the variations of magnetic field BZ during these events. You can see that during the growth phase, there is a very slow gradual evolution of the magnetic field. And there are only 3 periods when this evolution is rapid. The original event, which was discussed by Angelopoulos et al., the current disruption event, and the previous substorm activation. And final point, which is perhaps most relevant to this meeting, if you check the paper, the science paper, you can also see the plots of the map where the probes were mapped to ionosphere. And as you can see, surprisingly, all probes stretched along the tail had practically the same latitude. We made these reconstructions using our data mining procedure, and the result is entirely different. All these probes are stretched in in the range something like 4 degrees, not 4 degrees, no, yeah, 4 degrees. And moreover, you can see here the plasmoid, which appears in this case. It may be seen as a, in these maps as a bunching of the isocontours of equal distances. You know, the plasmoid is a closed field line region. It cannot be mapped to the Earth. It has zero area there. And numerically, it looks like a bunching of these isocontours. So we see here that we compare this with Z distributions here in the MLT CGM map with all sky imagers, which was provided by Tetsuo Matoba. And as you can see, during the first activation, the auroral images suggest that it is likely provided by the X-line reconnection near the Earth. During the second activation, as you can see, the source region is local. It is associated with the near Earth region. You can see signatures of beading here. And finally, during the main events considered by Angelopoulos in that seminal paper, the source of the activity may be much polarward compared to the plasmoid location. I actually finished my talk, and unfortunately I do not have any summary. I do not know how to summarize this very diverse message. Please feel free to ask me any provocative questions. Thank you.
Any questions?
Could I jump in with one question?
Go ahead,
this
Jason.
is maybe a very naive one. So, I mean, do you see the onset of reconnection or these thin current sheets as sufficient for substorm onset? And if so, how does it relate to the beating?
Jason, it is a very hard question. Honestly, I am not sure that if that reconnection is initial process, as when we simulate the formation of depolarization fronts and tearing instability, the first process which we observe is not the next line formation, not reconnection per se. The first process which we see is the redistribution of magnetic flux, which causes increase. The formation of X line is decrease of BZ, initial BZ. But what we first see is the increase of BZ and the transformation of the hump into a dipolarization front. Sometimes in the trailing region of this dipolarization front, you have an X line, but it is not necessarily a cause of this front formation. It is a concurrent process which is a part of the global flux redistribution. From that point of view, one cannot claim that X-line formation causes or is sufficient for the near-Earth dipolarization or for beading, etc. This is a combined process, very complex, and usually 3D and non-local.
Yeah, I think I understood that. I guess the main thing I'm confused about is the connection between, I mean, should I interpret the phrase onset of reconnection as substorm onset? That's, I think, my main confusion.
I would definitely disagree with equaling substorm onset and reconnection onset. These are definitely different phenomena.
Okay.
In most cases, substorm onset is accompanied or maybe even caused by the reconnection onset, but this is not just one-to-one connection.
All right. Okay, I thought so. Just wanted to check. Thank you.
Hi, Misha. And just to add on top of your answer to Jason's, I agree with what Misha said that I was going to actually touch on this when I talk in the next session. There had been this large conversation about what is the onset of the substorm. Is it the reconnection? Is it the brightening of the aurora? Is it the dipolarization? Is it the injection? And I think the community has more or less settled on the auroral brightening that then leads to the expansion of the aurora, and that usually also accompanies the dipolarization and all those other effects as well, because you can have reconnection that doesn't lead to a substorm. So then my question for you, Misha, well, first of all, this was super interesting. I loved your talk. And I was like, wow, that's so cool when you were showing your data mining agreed with Vasilis's reconnection location back from his 2008 paper. And I think I was so like enjoying thinking about that I didn't quite catch your immediate follow-on, which was saying how Tony Louie was also right with the current disruption. So what was the exact order that you saw there? Was there a substorm and then a current disruption and then Vasilis's reconnection and substorm? Like, could you restate
Christine,
that a little bit?
Thank you very much for your question, because I was confused myself very much. To be honest, when we developed WaveGrant with substorm data mining technology, I always dreamed about applying this technique to this event. And when we tried to do that, we discovered at first that the original technique was not applicable to that. It did not have enough resolution in time. You know, we usually average our binning parameters over something like half an hour. But you can see with storms, they were very localized and relatively weak. So we adjusted our technology, and then we discovered the following picture. We indeed resolved X-line reported in the Science paper, 2008. We indeed see that it is preceded, but not necessarily, it is preceded by the current disruption, by the rapid decrease of the thin current sheet which is in the system. But this thin current sheet was also preceded by another X-line, which was tailward of the current disruption region, which existed in the system already in the growth phase. And this is a typical situation with artificial intelligence. It shows you some sequence of events or picture derived from data which you still cannot understand or interpret. It does not help you in a sense that it does not answer the question. It does not resolve the dilemma which I mentioned in my first slide. We still do not know. We see this intertwining between current disruption and change of topology, and I have to admit that we still do not understand what is first and what is next. Moreover, we know now, thanks to Artemis, that everything may be governed by these processes outside of a region which we almost never considered. You remember Larry's favorite idea, or Tosh's favorite idea, that everything is provided by these streamers which come from the outer region. But this outer region has almost never been explored. Beyond 31 RE, we only have IMP8, Geotail, and Artemis, and that's it. But our reconstructions already show that there is substantial magnetic flux redistribution in that region, which quite likely drives all the processes in the more inner tail, part of the tail. Again, I believe this is what Toshi and Larry see in this streamer propagation from the essentially open-closed boundary to the Earth. Remember that half of this way from the open-closed boundary to the inner magnetosphere is still completely unexplored in situ. Thank you very much for your question, Christine.
No, thanks for answering, Misha.
Okay, Misha, one more question here. Thank you. Wonderful talk. So for the EASY mission, we essentially said that the physics is in the third dimension, the Y that we tend to ignore in the Y direction. In our old substorm current wedge picture, it is heavily tilted towards pre-midnight. It is not symmetric about midnight. So in other words, when many of these pictures you show, they're two-dimensional. They don't include the Y direction. Do you have any comments to, is there information in that direction?
Yes, sir. Thank you again for your question from my side. If you remember, Grant Stevens, in his 2019 paper, already drawn the substorm current wedge. What he did, he just took magnetic field configuration after the onset and subtracted from this configuration, from this magnetic field before onset. And we immediately observed this substorm current wedge. So we know and we agree with you that this is a global structure which has very clear geometry. But I cannot answer your question. We have never explored yet what is the evolution of this structure, in particular dawn-dusk asymmetry, and its dependence on, say, type of the substorm. There was no specific study. There was only one attempt to show that we are able to draw this substorm current wedge.
Thank you.
All right, thank you, Misha.
Thanks.
So we're 5 minutes over. I do just want to first, somewhere in this room, there are 2 volunteer graduate students. If you could just stand up, I think they deserve a round of applause for helping out with this session. All right, thank you to everybody for coming. Thank you to the panelists for your excellent talks. We're going to continue this discussion in this room in the next session after the break. Thank you.